Hello, welcome back. So today we shall start lecture 9 in this today, and we are going to basically talk about real semiconductor devices for RF electronics from today's lecture. So until last lecture we had basically had a recap of heterojunction physics, heterostructures, and then gallium nitride polarization. We also talked briefly about how the 2D electron gas is formed in an L-GaN HEMT. We outlined some of the basic properties of the electron gas in an L-GaN HEMT, but we did not discuss the transistor per se. And from today's lecture we will actually start delving into the semiconductor devices that go into RF and microwave electronics. Today's lecture will be on Varactor and Schottky multiplier. Actually today and the next lecture, lecture 9 and 10, we shall cover Varactors and Schottky multipliers. Okay. And here we shall also try to get a feel for what kind of real practical applications are these devices used for or are useful for. So going ahead, for whatever device we discuss, we also try to get a feel for the applications that those devices are being employed today, or what are the applications that they are promising for. That helps us calibrate ourselves with respect to the real world RF application, and that makes us do not lose sight of the eventual circuit or the system where these devices are going to be used. Okay. So we will come to the whiteboard PPT here now. So today is lecture 9 and then followed by lecture 10. We will talk about Varactors and Schottky multipliers. Okay. It is very important to understand these devices because they are useful in a lot of applications, and so we shall start from applications. What are the applications where we need this kind of for instance devices? Okay. So let us consider a receiver. So when I say a receiver, a receiver could be in any communication chip, for instance a mobile phone or a cellular base station or even a radar. Anywhere you want to receive an RF signal, you have a receiver, okay, a receiver chip. So the receiver, essentially what happens is that we shall not go into the details of the receiver, but here we will only talk about two components here where Varactors or Schottky multipliers will be used, and then we will discuss what actually are Varactors and Schottky multipliers. Okay. So this is the antenna, okay, this is the antenna where the signal, the RF signal is coming to the antenna, and you have a filter basically to filter out the unwanted signals, and you essentially do a very coarse or a rough filtering so that you are only selecting the frequency ranges of that are of interest. This is an LNA. LNA stands for low noise amplifier. So it will basically amplify the desired signal, because you see when you receive a signal it is of very weak intensity and it is corrupted by a lot of background noise that it has picked up, okay, the background clutter. So the low noise amplifier is a very critical component to essentially boost the signal level. And now comes two important components, one is a mixer and one is a local oscillator. What functions do these things do, and why do you need a Varactor or a Schottky multiplier there? Okay. So basically when you have a signal coming in at, suppose you have a signal coming in at say 15 gigahertz, that is your signal coming in, but it is an RF signal, but a lot of the processing, lot of the signal analysis and processing, it becomes difficult at higher frequencies. You can do it much easier with better performance if you bring it down to a lower frequency. So we call it IF, okay, intermediate frequency. So we want to bring it to a lower frequency, and for that we need a down conversion. When I say down conversion, it means whatever signal you are bringing in from the antenna, which is say 15 gigahertz, you want to bring it down to a lower frequency so that all your signal processing and subsequent all processing of the signal becomes easier. Okay. So I will have a local oscillator which basically generates an RF signal. Okay, it is called a local oscillator. It generates a signal at omega LO, that is the frequency at which it will generate the signal. Suppose it generates the signal at 13.5 gigahertz. So the incoming signal is at 15 gigahertz and the local oscillator is generating a signal at 13.5 gigahertz. What this mixer will do is that it will mix the two signals. So it will mix the 15 gigahertz signal with 13.5, it will create some harmonics and intermodulation products, like it will mix the signal. So you will get many frequencies, one of the frequencies will be the difference of these two, which is 1.5 gigahertz. Okay. You will get other frequencies that you can filter out, okay, that you will filter out, but this 1.5 gigahertz is a lower frequency and it becomes easier for you now to, for instance, process or do signal processing on those frequencies. Okay. So down conversion is very important, and similarly in the transmission you will have to do an up conversion, but mixer basically mixes two signal, for instance, and a local oscillator generates an RF signal which you are going to mix. But now suppose instead of 15 gigahertz tomorrow you have a signal at say 16 gigahertz. Now you have to tune the local oscillator accordingly. So this local oscillator, which is typically called a voltage controlled oscillator, a voltage controlled oscillator, by using an applied voltage you can tune the frequency to which you want to generate, the frequency that you want to generate. Okay. So by using an applied voltage you can tune. There will be a network, of course, there will be a circuit or a network that will help you generate this signal, but you need to tune, with respect to the voltage to be able to generate that local oscillator frequency omega LO. So what you need is basically a frequency multiplier, for instance, a frequency multiplier, I will come to all this, or a frequency a harmonic generator. Okay. What this means is that you can produce frequencies of RF signals of different frequencies using the local oscillator. Okay. And sometimes those frequencies may not be sufficient. So you have to increase the frequency to say 2 omega LO, which is called a frequency doubler, or maybe 3 omega LO, which is a frequency tripler. So those are harmonics of the original signal. So to generate those harmonics you need a device. So that device is called a frequency multiplier. Okay. You are able to get from omega, you are getting 2 omega or 3 omega or 5 omega depending on what kind of frequencies you want, doubler, tripler, quintupler, quadrupler, etc. Okay. So that is a frequency multiplier that is very important, and remember that frequency multiplier is not the only component in the local oscillator. You have an entire circuit and there are many oscillator circuits, but this frequency multiplier could be necessary in many application where you want to increase the frequency to multiple harmonics of the original frequency that the local oscillator is generating. Okay. In many cases, to tune the frequency, say you are going to tune it over a certain frequency, you also need a frequency tuner. In other words, you need a component such that by applying voltage you can tune the frequency. Now suppose you have in this local oscillator you have a resonance circuit. Okay. You can have a resonance circuit, and you know the resonant frequency of a resonance circuit is 1 by square root of LC. Now by any chance if this capacitance C can be changed by applying a voltage, you change the voltage from say 0 to -1 volt to -2 volt, and this capacitance changes, then this resonant frequency also changes. By doing that you are able to generate an RF signal of different frequency within a certain range. Okay. Within it is not arbitrarily high or low, within a certain range you can tune the frequency. So this is very useful for frequency tuning, and in the local oscillator you will often need that. So you need a device whose capacitance keep changing as a function of the voltage. Okay. That is for tuner, and you need a device such that from a frequency omega you can generate 2 omega, 3 omega, etc. Okay. That is a frequency multiplier. Okay. So you need these two kind of devices. Okay. I hope I am clear till now. At the same time you also have a mixer. In a mixer what you do is that you mix two frequencies, say you have omega 1 and omega 2, you will generate omega 1 minus omega 2, it will mix two frequencies. So you can call it as a frequency converter. Okay. So essentially you need actually many devices. You need a device that can convert frequencies, it can mix frequencies, it can generate multiple harmonics or higher frequencies, that will be useful in say millimeter wave, terahertz, etc. You need an element of tunability such that you can tune the frequency by applying a voltage. So it so happens that all of these things can be actually done by a capacitor whose value changes with voltage, and that is precisely a varactor. Okay. Varactor, and there is also varistor where you can change the resistor, but here we are talking about varactor where essentially it is a variable capacitor, a capacitor whose capacitance can be changed by applying a voltage, that is a varactor. And if this changes non-linearly, which it is, we will see that, then that non-linear variation of capacitance with respect to voltage will help you generate higher order harmonics, that is useful for frequency multiplication. Okay. It will also help you in frequency mixing. At the same time, because the capacitance is changing with respect to voltage, you are also able to change the resonant frequency and tune. Okay. You can tune it to any incoming signal. So All these functionalities are very much needed today, and that is why varactors and frequency multipliers are very useful in today's communication or any other RF electronic components. Okay. So, I hope it is clear till now. Just remember that in a receiver, and this is just an example of a receiver, there could be or there would be other application, a transmitter, a transmission receive module, TR module in a radar. There are so many different applications, but here I just give an example of a receiver. Okay. So, we do not have to discuss about low noise amplifier here or filter and other components, just to give an idea that this is how what happens in a receiver chain on a receiver component architecture. So, you have an incoming RF signal with which you mix with a local signal. The local signal is generated by a local oscillator, and when you mix them you generate lower frequencies, that is called down conversion. Your signal processing becomes much easier. Okay. So, now here is the thing. So, what is this varactor? We know that varactor is a capacitor whose capacitance can change with voltage and preferably non-linearly, such that you can generate harmonics. Okay. So, let me erase something that I have written here. So, anyways, this is a part of the recording, so you will be able to see whatever I have written here. Okay. But otherwise the text will not come out properly. Okay. All right, and it is fine. So, okay. Oh, I did not erase this, so maybe I will erase this again. Okay. So, essentially what happens is that you need, as I told you already, you need to generate higher harmonics, higher frequencies, and you need the ability to tune to certain frequencies. Okay. So, varactor is a voltage controlled capacitor whose capacitance changes non-linearly. Now, what is such a device whose capacitance changes non-linearly? A simple diode. Okay. A simple diode could actually be a varactor, a simple diode. Okay. A simple diode, as we shall see, a simple diode, if you plot the capacitance with respect to voltage, it goes something like this. Okay. It is a non-linear variation of capacitance with respect to voltage, and that non-linearity is good enough actually. Okay. So, a simple diode can actually behave as a varactor or as a frequency multiplier, but it is not that simple in real application. You have many more advanced versions of anti-parallel diode, double down conversion diode, and then you have different kinds of frequency multipliers, planar Schottky multipliers, and there are many complicated circuits in terms of local oscillators and mixers. You can implement them in chips, and so the varactor or the frequency multiplier will be a component of that entire chip, for instance. Okay. And what is the difference between a varactor and a frequency multiplier? Frequency multiplier is a type of varactor. A varactor is basically where your capacitance is changing with a voltage, and it can be a Schottky diode, for instance, it can be a PN diode, it can be even a MOSFET, okay, silicon MOSFET, or it can be even a MESFET, gallium arsenide MESFET. Wherever the capacitance changes non-linearly with respect to voltage, you can call it a varactor. Now, there are different kinds of varactors, of course. But if you want to multiply frequency, then typically people go for Schottky, it gives you faster because there is only majority carrier unipolar devices. So, Schottky multiplier is one of the application of the varactor, and when we use that as a multiplier, we usually call it as a multiplier. We do not call it as a varactor. We use the term varactor when you are using it, for instance, for tuning the frequency, for instance, then we call it varactor. But apart from this, there are other applications also, as we shall see. Okay. So, varactor is a nonlinear device, and by the word reactive I mean capacitive or inductive. The reactance is basically a capacitor. In this case we are talking about a capacitor, not an inductor. So, capacitance will change nonlinearly with voltage. So, harmonic generation is one application. I told you, you can generate double frequency, triple frequency, etc. And what kind of frequency you want to generate, that is also dependent on the application, and the circuit has to be designed based on that. It is not that simple. And when you generate harmonics, you may also get unwanted harmonics. For instance, you want only 3 omega, you want a triple harmonic, but you will also end up generating double harmonic, which you do not want. Those are, for instance, called idler's frequencies. Idler frequencies are those that will get generated that are maybe necessary actually for generation of the desired frequency of 3 omega naught, but which is itself not useful for the application. You do not want or do not get any 2 omega or double frequency either at the input or the output, but you will generate them. You only want 3 omega, for instance. This is just an example. Okay, there could be other cases also. And so, whenever you have idler frequency, you have to terminate them. What is meant by terminating? Now, here a little bit of microwave engineering concept comes into picture. Because microwave signals, are not something that you can easily understand in the concept of say Kirchhoff's law of applied voltage or current. If you talk about microwave signal, these are electromagnetic signals essentially that are moving in a either such a rectangular waveguide or some kind of waveguide or a some kind of a transmission line. So what happens is that if you have a transmission line, there is always an incident wave and then there is always a reflected wave. Okay, there is always a reflected wave, there is always an incident wave, because this is how the microwave, and this is from a certain load. Okay. So when I say terminate, you need to basically match the output impedance or the complex resistance, essentially impedance, such that you do not get any losses or not get unwanted reflections and those frequencies. In those if you have to properly terminate those idler frequencies at the frequency of 2 omega, you need to have a proper match so that you do not lose energy unnecessarily. Okay, otherwise you will lose energy in that 2 omega frequency also, which is not desirable in this particular example. So harmonic generation we have already talked about, we will discuss more. And frequency tuning in an oscillator, I already told you that a frequency has to be tuned, and so this is an important application of a voltage control capacitor. Another application is parametric amplification. What is parametric amplification? It is like amplifying a signal, but it is based on pumping the varactor diode with a certain signal and bringing in the input RF signal. There are two actually sine waves or two input signal. One is a pump signal of frequency Fp, one is a desired signal of frequency Fs, and under certain conditions that we will see, you can actually amplify the signal. We call it parametric amplification. It is not that widely used, but it is still very helpful. And of course, there are other applications like frequency conversion. For instance, you can mix or you can mix the frequencies, for instance. Those also can be done using a nonlinear reactance. As I told you, it could be Schottky diode, it could be PN diode, it could be MOSFET, a BJT. Wherever the capacitance changes nonlinearly with voltage could become a varactor and a frequency multiplier also. Alright. So now it becomes easier if we actually, instead of capacitance, if we talk about the reverse of capacitance or inverse of capacitance, which is 1 by CV, because capacitances add up in if you have series capacitance, then you add up in 1 by C1 plus 1 by C2 fashion. So to avoid that, you use the reciprocal of or inverse of capacitance, it is called elastance, so that the math becomes more convenient. You do not have to do this 1 by x plus 1 by y kind of thing, you can just do x plus y if it is inverse. Okay. So the inverse of capacitance or elastance is defined by the ratio of the voltage to the charge. Okay, and it is represented by the letter S. Okay. This is the representation of a ideal, or in a realistic you can say a varactor. So this is your voltage varying elastance, correct, and this is your series resistance. The series resistance comes up because in any practical real diode or FET or something, there will always be a resistance that is associated. It could be from the parasitic resistances, from the quasi neutral region, from the packaging, from wires. There is always this parasitic or this total series resistance that will come, and this is this creates noise. For instance, this puts a limitation on the frequency ranges. It has many limitations, but you cannot rule out the role of series resistance. Okay. Now, as I told you, if I take a simple Schottky diode, Schottky diode, then this is the schematic of a Schottky diode. You have a lightly doped layer, right, and then you have a heavily doped layer, which is on here you make an ohmic contact and on top you make a Schottky contact. Okay. So this has to be reverse biased to get a CV profile, to get a junction CV profile. So this is the band diagram, this is your reverse Schottky barrier height, this is your depletion region, this is your built in potential. So this is like the classic picture of a Schottky barrier diode, all of you know it. So if I plot the CV characteristics of this diode, how will it look like? This is how it will look like. Okay. From 0 to some reverse bias, it goes like that, right. So you can see that this is a non-linear variation of the capacitance, non-linear variation of capacitance with respect to applied voltage, correct. It is the non-linear response of capacitance with respect to applied voltage, and this will help you generate harmonics, and this will help you create multiplication of frequency or conversion of frequency. Okay. So what happens actually? So before that, we again will recap the very fact that the capacitor, we have to understand how actually this harmonics is generated. So we have to recap the basic equation for capacitance of a junction diode, and this is the capacitance equation of a junction diode. All of you know that the capacitance varies as the square root of 1 by the applied reverse bias. Okay. So, this is a reverse bias in negative, I mean the absolute value is being taken here. C naught is of course that epsilon 2 by something something. So, it is a constant, you do not care, this is the built in potential. So, essentially your capacitance is varying loosely as 1 by square root of the applied voltage, which is this. Okay. This is your nonlinear part. This is your series resistance, this is your ohmic contact, this is your Schottky contact. Okay. So, this is your capacitance and this is your depletion, correct. All this makes sense. And so, your electric field in the depletion region will vary linearly, and this is how you represent it. There is a varying series resistance and then there is a varying capacitance, which you call as maybe elastance. Okay. Now, if this is your capacitance, then the charge is obtained by, if you remember, charge is obtained by actually C dV, and so if you integrate this out, okay, if you integrate this out, it will look like dV by square root of VBI plus V applied bias. So, if you do an integration of that, it will become square root of VBI plus V applied bias. So, this is precisely what happens here. You essentially get the charge which is varies as square root of VBI minus, now here I am talking minus, actually you can give it plus if you are taking just the magnitude. Okay. Otherwise, it will be minus 5 volt for instance. So, it becomes plus anyway. So, that is why I am taking the magnitude, okay, because there is a minus in the reverse sign. So, this is your charge that you are storing in the capacitor that varies as a function of voltage, and you can expand that into a Taylor series like this, V plus V square plus V cube etc. Any function y equal to square root of a plus x can be expanded into a Taylor series like that. All of you remember that, I am sure. Okay. Now, if the voltage that you are bringing in here, is in the form of say cos of omega t, then because you have V square V cube, you have cos square omega t, cos cube omega t etc. You can express this in the function of cos of 2 omega t something something, cos of 3 omega t something something. So, these are the harmonics that you are generating essentially. This is the beauty of this nonlinear reactance, and this is the reason why you are able to, let me erase this, why you are able to actually generate harmonics. Okay. So, if V is a sine wave like this, then you are going to get higher order harmonics because of this V square V cube term. This is how you use the voltage controlled capacitor or varactor as a frequency multiplier. Okay. Frequency multiplier, and you get this higher order harmonics. Okay. So, I hope this is clear till here, right. Now, Schottky multiplier, and this is a very complicated circuit, and I do not want you to of course understand everything, and this is not a part of the course, this is not a scope of the course. This is just to give you a feel for kind of real circuits where, for instance, Schottky multiplier is used. A Schottky multiplier is basically you can generate harmonics from omega, you can generate 2 omega, 3 omega, 4 omega etc., and depending on what omega you want, you can filter out the other, you can terminate the idler frequency etc. So, Schottky multiplier could be useful in an oscillator. An oscillator can give you a frequency, but you need higher frequency. Okay. For instance, in this particular example, I have taken it from a paper published in 2008 for instance. In this paper, they have implemented this entire thing to actually multiplier frequency. So, here actually input RF signal is coming, and here of course the output RF signal is coming out. Okay. This is the input RF signal, and suppose the input RF signal is at some gigahertz. Okay. The thing is that you are actually using a frequency doubler. Okay. You are using a frequency doubler. This is a doubler diode, you can see that there are 4 diodes 1, 2, 3, 4. Okay. There are 4 diodes, and these are actually Schottky diodes. These diodes are actually Schottky diodes. Okay. There are 4 Schottky diodes. There are 4 Schottky diodes which are used to actually multiply the frequency to 2 omega. So, whatever frequency you are coming omega RF is going to 2 omega RF, is you are basically multiplying the frequency by creating harmonics. So, you use that kind of circuit, and there is a bunch of other circuits here, but you can and then this is a mixer. This is where you are mixing 2 different frequencies. Okay. And this is your LO circuit, the local oscillating circuit. Okay. So, the frequency multiplier could be a part of the local oscillator circuit, alright. So, the LO circuit will generate some signal, and you are basically going to multiply the frequency and mix with the RF. So, the mixers are used here, okay, the mixers are used here, and you are getting the output here. In a real application, this is how it looks like. Okay. So, you can see that this is actually this bar you see, it is on a chip, real picture. This is actually where the diodes are there, which are multiplying the frequency, okay. And you can see that this is the mixer, it is covered here. So, it is a mixer, and this is the output frequency. Okay. So, this is a Schottky diode in this case, but people can use PN diodes or even FETs and etc., but in this particular example this was a Schottky diode that was used for frequency multiplication. I hope this is clear till now. So, frequency multiplier is very important, and this is although it is 2008 paper, but it is still widely used. Even today frequency multipliers based on Schottky diodes are widely used for generating multiple harmonics of frequencies. Okay. Now, this is an oscillator circuit. Again, we do not have to understand the circuit per se, this is also from another paper. This is an oscillator, it takes a DC bias and converts it into, it is a DC bias, it will take a DC bias and convert it into an RF signal. But you need to tune it, because you need the ability to generate RF signal of different frequency within a range. Okay. So, you can see that this is a complicated circuit. However, these two are essentially your varactors. Those are voltage control capacitors or varactors, which could be transistors, which could be PN diodes or Schottky diodes. This will help you tune the frequency in this circuit, so that you can change the frequency over a range. Okay. As you can see in this picture, on the y axis is the frequency at which the oscillator is generating the frequency at certain frequencies at gigahertz, say 45 to whatever 52 or 53 to 62 to 63 gigahertz of frequency you can oscillate using this applied voltage. When you change from 1 to 3 volt, that is the voltage you are applying. This is called the applied voltage. And you are able to tune by doing this applied voltage change. You are tuning the capacitance here, this varactor, you are tuning that, or you are changing the capacitance. In turn, it is basically changing the oscillation frequency omega, because your 1 by square root of LC will change, the resonant frequency will change. So, you are in this circuit. So, you are essentially tuning the frequency over a certain range by changing the voltage that you are applying. Okay. And of course, this is varactor potential, that is fine. But so, you can see that in a real circuit like this, people actually use and this is the image of the chip that they actually fabricated. This from this paper that I am taking, in this paper they actually fabricated the entire thing, okay, using gallium arsenide technology, gallium arsenide MESFET technology. MESFET stands for metal semiconductor FET. We will discuss MESFET technology of course in subsequent weeks and lectures, but gallium arsenide is a very common and popular 3-5 compound semiconductor, and gallium arsenide MESFET has been around for a really long time, one of the oldest compound semiconductor technology, and even today gallium arsenide MESFET is still being used. So, the entire chip was made in a gallium arsenide MESFET, and the entire chip was made in a single die using a single substrate, which is gallium arsenide. It is called MMIC. MMIC stands for microwave monolithic integrated circuit. So, it is an integrated circuit IC, monolithic, microwave monolithic. Monolithic means that it is fabricated from a same die. You are not combining components from different sources and putting them together. That is like more like an integration in a package, okay, or you can call it a hybrid and a kind of a chip, but this is a monolithic. Monolithic means you are fabricating everything in a clean room, for instance, you are fabricating everything on a singular die in a wafer, essentially all resistors, capacitors, oscillators, mixers, frequency synthesizers, what have you, everything will be fabricated along in the same process flow along with the active transistors or diodes or whatever on a particular wafer. You are not integrating externally sourced resistors or passive components, you are not integrating anything external. That is called MMIC. It makes your chip very compact, very small, okay, and it is a very good form factor that people like it. So, MMICs are very widely used in military, for instance, or strategic radar, or even in satellite transponder, etc., etc. However, non MMICs or hybrid kind of chips are also very widely used in many applications. However, in this particular example they have implemented this entire oscillator in an MMIC of gallium arsenide, 4 gigahertz gallium arsenide MESFET technology, they implemented the chip and it looks like this. So, we do not have to understand each and every conductor. For instance, this could be a spiral inductor. Okay. On the chip they have made an inductor by making a spiral line, a spiral line goes like that and it can be an inductor. It is fabricated on the chip along with the same process flow. So, it is a spiral inductor. You need an inductor of certain nanohenry, for instance, in your circuit. This is a varactor, this is your FET, this is a 4 gigahertz MESFET and the total size is 0.9 by 0.9 millimeter. Okay, very compact, you can see that. It is a very compact 4 gigahertz MESFET. So, the varactor here is also gallium arsenide MESFET, it is not a Schottky diode. So, this varactor will basically tune the frequency in this, as I have told you. Okay, and that is by changing the voltage you are able to change the oscillation frequency because of the varactor, and so the varactor is a very important component that is sitting in a circuit like this. Okay. So, this is about how in a real scenario how a varactor or a MMIC chip, how a varactor is incorporated in an MMIC chip. Now, we have to talk about the varactor model. Now, because we have got an overview of the varactor and the tuning of your capacitance, we have talked about the harmonic generation, you can get 2 omega, 3 omega, etc. Those are that are not desired are the idler frequencies which you have to terminate. You have to match the output accordingly at different frequencies so that you do not have extra loss, you can get better conversion efficiency. So, in all these cases, of course, if you are talking about a local oscillator, what matters also is how much output power you are getting. Okay. So, how much output power you are able to deliver, even for frequency multiplier, what is the kind of power levels we are talking about in frequency multiplier. Can you get 3 omega or 4 omega or 5 omega signals, what is the power level. So, these frequencies can be very high, they can go up to terahertz actually, okay, sub terahertz to terahertz, and people can get tens of milliwatt to hundreds of milliwatt at very high frequencies, that is the frequency conversion. Okay. So, efficiency of frequency conversion, the power that you are getting at different frequencies or not, you are terminating at different frequencies, all of these are very important, and one of the important thing is called a Q factor. Q factor is basically how much energy you are delivering divided by how much energy you are getting lost. Okay. So, how much energy you are you need to minimize the energy that you are losing, how much energy you are storing divided by how much energy you are losing. So, Q factor, the higher the Q factor better it is, and a lower Q factor means it is not a good thing. Okay. So, Q factor, the conversion efficiency, the power output that you are getting at different frequencies like 3 omega, 4 omega, all of these are figures of merit, and in a place like oscillator there is even things like phase noise, okay, which is also a figure of merit. Okay. So, there are many things actually that are involved in all this RF components and chips. We cannot cover everything in a course, we are only trying to understand the varactor and frequency multiplier here in the context of a real chip that is being developed. Okay. The next thing that we will have to talk about is actually to understand the working of a varactor. Okay. The frequency, we understand it is a Schottky diode or a PN diode or whatever, but how do you model that or how do you capture that. So, I told you instead of a frequency, if you can plot the frequency as a function of voltage, it will go like this, but instead of that I will plot elastance which is 1 by C. So, it will go like this, right, and this is going because this is a forward turn on and you do not want the forward turn on to be reached, and this is beyond this it will break down, okay, because you have a maximum reverse bias you have reached. So, this is the range at which you will have the swing. This is the voltage swing over which you can make the elastance swing. Beyond this part you will have a huge forward leakage, forward conduction, and your capacitance behavior is lost. Beyond this point you have breakdown, so your device breaks down anyways. So, your swing is limited by the forward turn on and the breakdown, that also determines therefore the elastance swing. Okay. So, capacitance is maximum at 0 bias. So, you can see the capacitance is minimum at the elastance is minimum at 0 bias. Okay. And of course, this part is positive, so it does not count, and at this point actually the capacitance is minimum, in other words the elastance is maximum. Okay. The elastance is maximum. This is for a typical PN diode or a Schottky diode, it will look like that. This is for something called symmetric diode or symmetric varactor diode. What does symmetric varactor diode actually mean? We will come to that. It could be a heterojunction barrier diode or heterojunction barrier varactor. So, in a symmetric diode you get basically the same kind of a behavior on both positive and negative side of the voltage axis. So, within a certain range you get the same behavior, and this is possible in a quantum barrier, heterojunction barrier, Schottky varactor for instance. Okay. So, essentially what is happening in here is that your elastance S is actually a function of time, and you need to terminate the frequencies appropriately in order to get the better efficiency, the best efficiencies and the best power. So, the output and the input as well as all the unwanted frequencies have to be terminated appropriately. Okay. And so, at all those idler frequencies the network should be able to terminate the varactor, and wherever frequencies are of interest either at the input or at the output the network should be able to couple the varactors to the sources and loads at the desired frequencies while terminating it at the idler frequencies. So, appropriately. So, this is very important for the proper operation of a varactor, you should keep that in mind. Okay. Now, this is just a Schottky diode, but it could be even a PN diode for instance, and Schottky diode is you can make it on silicon, you can make it on gallium arsenide, but quantum barrier diode or heterojunction diode you can even make it on L-gas system, and you will see that you actually get a symmetric kind of a elastance behavior with respect to voltage on a symmetric diode. Okay. And symmetric diode like this only produce odd harmonics. The mathematics tells that there is only odd harmonics, which means you only get 3 omega or 5 omega etc. You do not get 2 omega, 4 omega etc. and that is helpful in certain applications. You only need 3 omega or 5 omega, you do not need the odd harmonics. So, it is very easy to filter those out. So, symmetric diode is very useful in those cases. Okay. So, I think we can end the lecture here today for lecture 9. About the introduction to varactor and frequency multiplier, and we tried to get a feel for different kinds of chips, VCO chips or mixer, where these kind of things are applied. Even today they are useful. We do not have to understand the chip, but we have to just appreciate that in an entire oscillator chip there is a voltage tuning component which will vary the capacitance in the varactor, and you can tune the frequency over a certain range for instance, or you are able to use a frequency Schottky diode frequency multiplier where a single frequency is multiplied at higher harmonics to generate higher frequencies, and these are useful for local oscillator, these are useful for frequency converters, frequency mixers. So, in all these applications varactors, Schottky diode frequency multipliers are very useful. Okay. So, we still have certain more things to learn about varactors and Schottky diodes. Okay. It is not the end of it. So, we will conclude that in lecture 10 next. Okay. So, with that we will end lecture 9 and you have a nice day. Thank you.